I want to talk today about one of the properties of waves that's exhibited by electromagnetic radiation. That's refraction. You've seen refraction before in many instances. One of the cases that you've seen refraction is what you see on the board right now. That's a pencil in the water. That pencil appears to be bent. Clearly it's not. It just looks to be bent. When we put a pencil in water and look at it from a certain angle, it looks to be bent because there is light reflecting off of the pencil inside the water. That light has to leave the water and go back into air. And when it does, the light changes direction. The change in direction of the light is defined as refraction. That tricks our eyes and our brains into thinking the pencil in the water is somewhere where it's not. Clearly, the pencil that's in the water is going to follow in a straight line from where it was before. But it looks like it's bent because the light changed direction when it left that water-air boundary. Now, why does it do that? Why does the light, or any wave for that matter, change direction when it goes from one medium to another medium? If you were in my class of Physics 20 last year, I would have went through this analogy with you when we talked briefly about refraction. But I'll go through it again for the benefit of those who haven't seen it and just to remind those of you who have seen it. We've got a parking lot here. It's paved. And then beside that parking lot, we've got a swamp. For whatever reason, we've got soldiers marching in this parking lot. 7 soldiers. They're all in a line, and they do what soldiers do, right? They all march in stride. Now, if we look at them from above, those soldiers kind of look like a line. We'll call it a wave front, a wave of soldiers, a wave front of soldiers. 3 seconds after these soldiers are in this position, they've marched forward, so they're now in these positions. Except this guy. This guy at the end is now in the swamp. So what's going to happen to him? Or her? He's going to slow down, right? So he's still going in a straight line, but he's slowing down. If we join these together again and make our wave front, then it's going to look something like this. 3 seconds later, soldiers are in a new position. Going to look something like this. Now we've got 2 soldiers in the swamp that are going a little bit slower. They're trying to keep up, but they can't. So the wave front's going to look like this. 3 seconds later, soldiers are in a new position again. Now we've got 3 soldiers in the swamp. This guy's going slower. This guy is still going slower. This guy is still going slower. What does it look like? It looks like this. This is a good analogy for refraction. What's happening here? Well, when the soldiers marched into the swamp, they changed speed. As a result of that speed change, the direction of the wave front changed. When the speed of the wave changes, and the speed of the wave does change when it goes from one medium to another, then the direction of the wave will also change. Now, what else changes? Look at the picture. It's staring you in the face. The speed changes, the direction changes. What else changes looking at this diagram? What do we define this distance as from wave front to wave front? We call it the wavelength. What do we find this distance as from wave front to wave front? The wavelength. But the wavelength is decreased, right? When a wave goes from one medium to the other, the speed changes, and that causes the direction to change. And the speed changing also causes the wavelength to change. Now, you might remember from Physics 20, there's one thing that doesn't change. Once the wave is produced, this one thing always remains the same. I frequently forget what it is too. What is it? Energy. No. Frequency. Yeah, it's frequency. These things will change. They all change because of this one. The speed changes when it goes into a new medium. Therefore, the direction changes and the wavelength changes as well. This doesn't. Okay, this one stays the same. Once a wave has been produced, the frequency always remains the same. Okay, that's refraction. So we're going to define refraction as the bending of a wave when it passes from one medium to the other. This is a property of waves. It's exhibited by EMR. We learned that yesterday. The bending of a wave when it passes from one medium to the other. And why does that happen? Happens because the speed changes. Another term, the index of refraction. The index of refraction, or refractive index sometimes it's called, is defined as a ratio of the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second always, to the speed of light in whatever medium you're trying to find the index of refraction of. Let's say we've got glass, and the speed of light is 2 times 10 to the 8 meters per second, because that's what it is, roughly, in glass. Well, then the index of refraction would be 1.5. 3 times 10 to the 8 divided by 2 times 10 to the 8. Ratio, synonym for ratio is divide, right? So divide 3 times 10 to the 8, the speed of light in a vacuum, to the speed of light in the medium. The index of refraction also gives us a measure of how much light bends. The bigger the index of refraction, the more light will bend. The smaller the index of refraction to a value of 1, the less it bends. If the index of refraction is 1, no bending happens. But as you go up from there, we get more bending of waves, or specifically in this case, light. What do you see right there? I call it refraction. Sorry, you call it a rainbow. We could call it refraction because that's exactly what's happening. We see a rainbow because of refraction. There's a specific process that's actually taking place, which is multiple refractions, that we call dispersion. You guys have seen this before in a rainbow, but you've also seen it in other places as well. If you walk out of the school at a certain time of the day, and it's a certain time of the year, and the sun is bright, the sun comes through the windows at the top of the atrium, comes down and goes through that corner glass display case by the cafeteria, and forms a beautiful spectrum, or a beautiful rainbow on the floor. It usually happens at about 3:40ish, 3:30, 3:40. And again, it's only if the sun happens to be bright, and it's only at certain times of the year that it does that. That's refraction. And specifically, it's called dispersion because we get multiple refractions taking place. It's exactly the same phenomenon that produces the rainbow. And it happens because each material, glass, plastic, water vapor, right, which produces rainbows, has a slightly different index of refraction for each different frequency or each different color. So when white light, or sometimes we call it polychromatic light, what does poly mean? Multiple or many. Chromatic means color. Polychromatic light, many colors. When polychromatic light, or many colors, or white light comes from the sun, appears to be just white or yellowish light, consisting of many colors, encounters something like a prism, or water vapor, or water droplets, or that corner display case out by the cafeteria, each different color bends a different amount because there's a different index of refraction for each different color. The material that it goes through has a different index of refraction, albeit a slightly different index of refraction for each different frequency or each different color. That causes each one to bend a different amount and split up. So we see, well, if you're a Pink Floyd fan from 40 years ago, Dark Side of the Moon, anybody know what I'm talking about? Yes? It's on the album cover and on the t-shirts. Where you see this white light, which is all the colors really just combined, polychromatic or white light, going through a prism and bending different amounts. It bends different amounts because the prism has a different index of refraction for each different color. With a different index, remember we said index of refraction is a measure of how much light bends. So if there's a higher index for blue light than there is for red, then blue light will bend more than red, and it will split up, and it'll form this continuous spectrum. Call it a continuous spectrum because it's all the colors of the rainbow just kind of continuously changing. It's not distinct colors. It's one color kind of transitioning into the next color. We call it dispersion. It's refraction, but this specific thing going on where we have multiple refractions is called dispersion. And you can see on the diagram over here that violet light refracts or disperses the most, and violet light has a higher frequency. So we would say higher frequencies disperse more than the lower frequencies. Or you could say, I suppose, lower wavelengths disperse more than higher wavelengths. All right, last thing that I want to do with you today, I want to draw a picture of the Earth. Now, this diagram is not going to be to scale, and you're going to see that in a second when I draw a picture of the sun here. The sun's over here, and it's smaller than the Earth, which of course we know is not the case. It's also a lot further away from the Earth. We know that the sun generates white light, and that white light comes toward the Earth, but as it does, it's going to encounter the Earth's atmosphere. The Earth's atmosphere is composed of many, many different materials. Nitrogen gas, it's mostly composed of nitrogen gas, right? But it's also composed of oxygen. It's composed of water vapor, of dust, of all kinds of different elements and compounds and so on in the atmosphere. Carbon dioxide in the atmosphere and so on. When that white light or yellowish light comes from the sun, encounters the atmosphere, it refracts because it's going from the nothingness of space to the somethingness of the Earth's atmosphere. It refracts. But just like with glass and just like with plastic, the Earth's atmosphere has a different index of refraction for each different frequency or each different color. So what we end up getting is a process of dispersion taking place. We get red light dispersing the least, right? High frequencies disperse more than low frequencies. So what we would see is red light bending right here. We would see green bending more, blue, indigo, violet bending more. So it would end up looking something like this with a bunch of colors in between. Now, I want to ask you a couple quick questions. If there's a guy standing on the Earth here, a really, really tall guy, evidently, what time of day is it? Nope. What time of day is it for that guy? The sun is pretty low on the horizon for that guy, right? It's either sunrise or it's sunset, right? What color is the sky sometimes at sunrise and sunset? Reddish, because red light refracts the least or disperses the least. What time of day is it for this guy right here? Standing on the Earth there. Sorry? Yeah, it's noontime or daytime sometime, right? What color is the sky? He looks up, what does he see? He sees the yellow sun, right? But what color is the sky? It's blue because blue light refracts, or blue, violet, blue, indigo, and violet refracts the most. So that's why the sky is blue, but that's why the sky is sometimes reddish too. And sometimes you can get hues of other colors mixed in there as well. Does that make sense?